Mhm. Hi guys. So today we were to go through. Actually, this is the first live stream, and we wanted to go over a few things that came across, especially when it comes to coding and coding challenges that we encounter. So this is going to be a series that we'll be going through. I and I'm joined as well with Mike. You can check his channel down on the description below. His channel is Mike Madhu KE. Just make sure you go and subscribe to him. So the main challenge was that I was trying to do some general mathematics. Actually, I had an app that I was working on, and it involved doing calculation for the amount. It was like it was managing currency. I don't know how best to explain that, but there's more of a financial application. So the challenge was that when I was doing the calculations, the math wasn't adding up. That makes any sense. In terms of this, if I did the same math using a calculator, the output was always different. I'll show you an example right now. And for example, in JavaScript, if I do this 0.2 as such, the output will be something like that. But just for the demo, it created just a playground for us to test. And then save that. As you can see down
Sorry, James,
here,
I can't see your
it's
screen.
always
Um,
um I believe you're sharing the wrong screen based on what I'm saying. Double tap my stream.
mhm. Just a second.
Can you see it? The other one, not that one.
Which one? This one. This one. This
Um
one is me.
oh sorry. You should see it now.
Okay.
Check what stream. The other one.
Yeah, just a second. Yeah, there we go.
Yeah. So as you can see on my screen, if you try to add a zero point 0.1 plus a 0.2, you'll always get this weird number. Um,
Yeah, that's good.
and then at first, actually, I thought that this was a JavaScript problem. Actually, for real, I was living okay knowing that this one is just a JavaScript problem because I always assumed at the back of my head, since most of the things that we do in terms of doing calculations or analysis, we always use Python, or maybe let's say R, the calculations in maths that will always be accurate. And then I just sat
Mm-hmm.
down and thought, maybe what is the harm in actually to check what's the same output on those different languages, and which I went ahead and I did try that. For example, if I do the same on Python, uh, select they say I still get the same output. Now that got me even more curious. So I didn't stop there, actually. I decided to even try one more language just to confirm. So this one was using Dart. I'll still run the same code. That will be zero point 0.1 plus zero point 0.2. Uh, Still, the chances that I'll still get the same output.
Yeah.
So,
Hmm.
what do you think could be the problem?
Um,
Maybe Miko, you can go ahead and take us through what you think. Or is it something that has always been there? I don't know. I am yet to find out because now I was more curious on why is this happening.
Yeah, first of all, I'm usually a fan of low-level languages, so my first thought will be, this sounds like a high-level language problem. So maybe I can try on let's say C++, low level. Just going to create a small solution here. Um,
Hmm.
create a new project. Just going to create a test solution and then see what it is because that's very weird. I
I know.
how and it's across all languages. Maybe it's in all. I don't know.
Maybe, you don't know. Yet to say. Because I thought because of how simple it is, at least I should be getting, since, for example, a calculator is made by a programming language, so such things should not actually be happening.
Yeah, and that
If
could
that
be
makes any
very
sense.
yeah, it could be very dangerous even.
Yeah, I know.
Because if you're making a real world application expecting it to be accurate, then if that is happening, that would be very terrible. Okay, so here I am. Um, so we have we just print 0.1 plus 0.2. Simple as that.
Yeah, yeah, but actually, just imagine if you're doing, let's say, a banking system, and then you're just trying to do the basic like maths for each time they top up the account balance, or they do a withdrawal. You'll either be stealing from the client, or the client will be stealing from you, if that makes any sense.
Yeah, true.
So
So
it will be ironic in some kind of way.
okay. Yeah, very, very true.
Hmm.
And you could, yeah, maybe you can even get jailed for changing figures. Well, it's not really a
Yeah, I
thing that's
know.
happening. Oh, look, okay, the result I'm getting here is 0.3.
Yeah.
Um, however, let me just check with the debugger because I know
Mm-hmm.
sometimes C++ truncates when you're printing out. So let me just do it with variables.
Hmm.
So I'll just declare a float, let's say A, float B, and then I'll just assign it to another float C, let me call it A plus B or something like that. And then, oh, there's an error here. And then I'll just put a breakpoint and then look at it from the debugger so that I can look at the memory. Oh, look at that.
Yeah.
So
Okay.
you can see 0.1
Yeah.
has a funny figure, 0.2 as well. Let me just move this second section.
Hmm.
Oh, look at that. When you're adding
Hmm.
them, look at this. What is
Yeah.
this?
No, it's weird.
Okay.
That's really like that's very weird. 100%. Like, I am. So does that mean that
Hmm.
at the point where you're running, somehow at the end of it, it's getting truncated, the rest of the numbers at the end?
I don't think so. I mean, for this one, it's just because I'm printing. When it's printing, it will truncate, but it's not that the actual value has been truncated.
Hmm.
So whatever is stored in memory is the actual value. Whatever we're seeing when it's printing
Okay.
here, um, let me just go
Hmm.
to this. This output is not what is actually stored in memory because, of course, we have seen
Okay.
those extra digits. So this is just what we're
Yeah, yeah.
seeing, but it's not what is actually in memory. So I'm curious. Let me just try to see online.
Mm-hmm.
Um, First of all, how do computers convert data into binary? Um, okay. Of course, we know. I don't know if you remember from school, converting. I remember us doing conversion for integers, which was very straightforward, but I don't remember for
Yeah.
floating point numbers. So I remember for
Okay.
oh, here we go, floating point numbers. I don't know if you remember
Mhm.
for integers.
Yeah, I do. I do. I do. But just for the sake of whoever is watching, you can just try and explain it out.
Yeah. So let me just open Notepad here. I hope it will make sense. To increase the size a little bit. So if, for example, you're trying to check the binary digit of 4, so every time
Mm-hmm.
we'll just divide it by 2 here. Then here we'll get
Mm-hmm.
0, and the remainder will be 0. I mean,
Okay.
sorry. It will go
Is it?
twice. Remainder will be 0. My bad.
Mm-hmm. Yeah.
Then now we'll
Yeah.
pick this 2 here. So 2 divide it by 2, we get 1, remainder of 0.
Mm-hmm.
Then we take 1, divide by 2,
Mm-hmm.
we get 0, remainder of 1.
Get
And
zero
then our binary
and
value will be this digits going up. So 100 base 2. Uh, so now this
mm-hmm.
will be our
Mm-hmm.
our binary number. This is number 4 in binary. So now if
Okay.
mhm.
Sorry.
If you're converting
Maybe just to clarify something.
yeah.
Um,
Sorry,
can you hear me?
I think I lost you a little bit, but you're back now.
Okay. I was saying, so at the point where you're dividing, you're always dividing the whole number. Is it the remainder or is it the value that you've gotten? I think I lost connection. Just a minute.
Yeah, yeah, I
Connection
can
to
hear you. So
YouTube.
it's there's a quotient and there's the dividend.
Yeah.
So you take the quotient. That will be. I don't remember if I'm doing the right. I'm saying the right term. It's been a while since I was in school. Let me just confirm that. Wow. The result that you obtain by dividing one quantity by another, yeah, the quotient. So this two that you get is the quotient, and then of course you have the remainder. So you divide the quotient consecutively by 2 until your quotient becomes 0. That's how you go about it.
Okay.
Yeah.
Okay.
So now for
Just, it seems I'm having issues with my internet. If I'm not wrong. Give me a minute. Just one.
okay, meanwhile I'll be checking how to calculate
Yeah.
binary of floating point numbers.
Yeah, I think I should be back now. I don't know if it's still my over.
Okay. You good on your end?
Not yet. Just let me restart the stream.
Okay, no problem.
Mm. Did you find you can continue? I have to reset the stream and then we can continue. So
Okay.
gonna take me 1 minute, but I'll be back.
Sure. Well, for the viewers, as James fixes his connection, so um, from this site here, log2 base 2, they tell us to calculate the binary of a fraction. You multiply by 2. So it's kind of the opposite process from what you've done. So in this case, if, for example, we had 0.25, we'll multiply by 2, and then we get 0.5. So in this case, uh, we'll take this value here will be what we take, the value of before the decimal point, and then we keep multiplying here. 0.5 times 2, we get 1.0. Yeah, so let me see. So we do this until it becomes 1. So, which means for this one, for so now the other kind of changes. Since we are for floating point numbers, instead of taking them down going up, we take it up going down. So this one would be 0.01 in binary. That would be the value in binary. Let me just use three to represent the binary value. So now this begs the question, since our problem comes from this 0.1 f, the floating point for 0.1, I wonder what our 0.1 should be. So if we do it manually, we'll have 0.2 and 0.2 times 2, 0.4, 0.4 times 2, we have 0.8, 0.8 times 2, we have 1.6, and then in this case, since we're taking this value, we just remain with the decimal value. So we have 0.6 times 2 equals
Mm-hmm.
1.2. So now we go back to 0.2 times 2, 0.4, 0.4 times 2 equals 0.8. I don't know if you are back with us, James.
Yeah, I'm back. I'm back.
Oh, nice. Um, I don't know if you have noticed something that's going on here. We've started repeating our values. I don't know if you've noticed that.
Mm-hmm. Yeah,
So
yeah,
we started getting
yeah.
0.2, and now we are repeating. So if we continue here, it will just continue being 0, 0, 0, 1, 1, 0, 0, 1, 1, and so on and so forth. So just a repeating sequence here.
Mm-hmm.
Um,
Yeah.
so I'm guessing this is where the issue comes in. I would like to believe so.
Yeah. Okay.
So I don't
It
know.
will make
Yep.
sense as well, as in it will also make sense as to based on that calculation that you just did, since it's a recurring, the machine kind of truncates it to something like that. I think.
Yes.
I'm not sure. I'm assuming. Mm-hmm.
Yeah, probably. So let me see. I'm just curious to see whether whatever we've calculated here is what the machine will show us. Like if we put it um, in code, um, if you request to see.
Mm-hmm.
So just googling here how to convert. Okay. So just copy this as is. Let me just replace that. So since we're looking at 0.1, I'll just do that. Then include this bit set. Okay, so what this is doing here, we are converting this float that we have here, 0.1, into the binary value that is now stored in our machine. So if I take a look at the value, let's see what it will
Okay.
print out. Okay. This is interesting. Look at this. This is not the same value as
Mm-hmm.
even for starters. It's starting with one. Let me just zoom it so that everyone can see. Oops,
Okay.
zoomed a bit too much. Um,
Mm-hmm.
Look at this. So ours is starting with one, and this one is starting with. I mean, sorry,
Mm-hmm.
ours is starting with zero. This one is starting with one, which yeah, that doesn't make any sense. But
Yeah, it doesn't.
I'm actually noticing there's this. Okay, there's a bit of familiarity. If you can look at this, there's this 11, let me just call it 11 0 0 11. It's kind of repeating
Mm-hmm.
here.
Yeah.
So maybe it's the same. I don't know. Maybe, okay, I don't know. Maybe the machines
Mm-hmm.
saw it in a different way. So
Mm-hmm.
let me go back to this first site. Let's see. So for floating point numbers, so according to this site, root.hashnode.dev, so they're saying there's a certain way that floating point numbers are
Mm-hmm.
stored, and it's not the way we
Mm-hmm.
calculate it per se. So
Yeah.
so they're saying assign an exponent, mantissa. That's a lot of jargon, but maybe we can go to this example. So a single bit that represents the sign of the number.
Mm-hmm.
Okay. So having read this a little bit, so I think I can get a bit of an explanation. So it seems that we are okay. The first bit, this one, the first
Mm-hmm.
bit will represent
Mm-hmm.
whether it's positive or negative, which would make sense because
Uh,
if we just have a number, we don't know whether it's positive or negative. So the first
yeah,
bit,
yeah, yeah, yeah.
whether it's positive or
Mm-hmm.
negative, so 0 for negative, 1 for positive, and then
Mm-hmm.
we have an exponent. So an exponent is a fixed number of bits that represents the magnitude of the number, typically in scientific
Mm-hmm.
notation. So I think we
Mm-hmm.
know the exponent for like the normal type of exponent. So for example, if it's this 0.25, usually we'd put
Mm-hmm.
it like 2.5 times 10 to the power of, is it negative 1, right?
Mm-hmm. Yeah.
Yeah, to the power of negative 1. So decimal this is decimal representation. So
Yeah.
for binary representation, so if I take this for example and we try to do it in to do an exponent for it, we'll get
Mm-hmm.
1.10011. This is a point. So we've moved the decimal place from here. Let me just represent it correctly. So we've moved it one, two, three, 4 times. So
Four,
this will be
4 times.
times two, since our base, we are in binary, so our base will be 2, not 10. Then to the
Mm-hmm.
power of 4. And then you notice for this one, even though we're
Mm-hmm.
moving this direction, it will this will still
Mm-hmm.
be positive, not a negative like in the
Mm-hmm.
decimal, because it's kind of like we have inverted it. So the same way that when you're calculating the binary for a whole number, we are dividing. When you're calculating for for a float number, we are multiplying. And then when you're picking the
Mm-hmm.
values, you're picking from for decimal, we're picking, sorry, for whole number, we're picking from bottom to top, And then for this, we're picking for decimal, I mean, for floating point numbers, you're picking,
Float. Yeah.
yeah, top to bottom. So,
Mm-hmm.
so now this will be the way it will be represented as an exponent. But then
Mm-hmm.
there's something here that is I had read it before that they usually add a bias. So a bias. I don't know if you know this, but our the floating point numbers are usually 32 bits. Like how they're stored in memory is 32 bits.
Okay.
Yeah. So
Mm-hmm.
so the bias for a 32 bit will be 127.
Mm-hmm.
This is 2 to the power of 8
Mm-hmm.
minus 1.
Why?
So 8, 32 bits, that's because 32 bits is 8 bytes.
Yeah.
So 8 bytes, so 2 to the power of 8 minus 1.
Mm-hmm.
So
Mm-hmm.
that's how they calculate the bias. Um,
Mm-hmm.
so now this bias 127, they add it to, so our exponent in this case will be this 4,
Yeah.
right? So
Mm-hmm.
whatever is stored in memory is now 127 plus 4.
Mm-hmm.
So this is something interesting because at the first time when I saw this, I was wondering what is that bias for? I mean, why do you need to add 127 plus 4? But then I read an explanation that said it will allow us to know whether it's positive or negative. So
Okay.
if this exponent is positive, then our value will be above 127. If it's negative, then it will be below 127. And
Mm-hmm.
whatever value we get will still be within the range of those 32 bits. So that's how
Mm-hmm.
it's stored. So coming back here, so that will be our next. Is it eight bits? Let me see. So now that one, let me just use a site here to convert. So for hours, 32, 127 plus 4 will be 131. Right. So let's see
Yes.
what 131. I'll just use a calculator. From decimal to binary, we're converting 131. Convert. So it's this 0, 0. Mhm. Oh, this. Wait a second. It's not adding up.
Up to like based on um
This one.
based on what I was looking at before, I could see like it was matching. We'll go back to your term, yeah, and also your notepad.
On my notepad. You just put them all
If
somewhere
you
we
could,
can see.
yeah, if you look at what you have selected on the notepad,
Hmm.
as well as you look at the output that you have on on the terminal, up
Yeah.
to their match is just that doesn't have the decimal point.
Yeah, that's true. The first bit.
Yeah, so and then you said, remember you said that after that point the number now keeps repeating itself.
Yes. Yes, it does.
I the only place now that actually it does it now it goes back trying to recreate that thing over and over again. Now
Yeah.
this one even becomes more confusing.
So okay, the part that I see is repeating. Let's see. Supposed to start with 1 1 0 0 1 1 0 0 1 1 0 0 1 1. Maybe they add something extra, but
No,
I'm expecting that we should also have this value somewhere. Or maybe is it
that
that they add,
I
because
can't
I'm also seeing
see.
this. I don't know if it, let me increase the size of this one, because I'm also seeing this
Yeah, you
value
can see it.
here.
Mm-hmm. Yeah. 1, 2, 3, 4, 5.
Those are 5. This is
No, it's
4.
not that. That
No, it's not.
has, yeah, that's 4.
Huh. Interesting.
Yeah.
So the exponent determines. Okay, maybe it's because let's see if we finish this, we can get the exponent determines the scale of the number, indicating whether the decimal point should be placed. A mantissa, also known as a significant a fraction, this
Mhm.
component represents the significant digits. The mantissa is a variable length sequence of bits that contains the digits of the number. Okay, the mantissa is basically what we originally had. Um,
Mhm.
okay, I guess this is. Huh. I would like to see the actual calculation. An example with an actual calculation so that because now at least we have an explanation, but the number we are seeing here is not what you're expecting. At least we know the
Yeah.
first one is a
Yeah.
bit. Let's see. So how computers
Mhm.
store? It's about how they store the floating point numbers.
Mhm.
Oh, this looks. Oh, nope. uh, okay, let's see this one. Let's close that. Okay. I guess this is the standard for IEEE 754 standard is what is used. Yeah, so the sign bit. Okay, so here's a bit of a
Mhm.
visual explanation. So we
Mhm.
have the first bit is a sign bit. I think we already understood how that comes about.
Mm.
Yeah.
Yeah.
Then we have the exponent, which is the next 8 bits. Okay. So we have the exponent. So 1, 2, 3, 4, 5, 6, 7, 8. Let me just copy this
Mhm.
and see what
That's
its value is. So from binary to decimal, let's take this
mhm.
and convert. 155.
How did they get to 155?
Yeah, that's a question. Because now we're expecting it to be, huh? Let's see. Let's see if they can give an explanation. Hmm. Okay, so here's a bit of a visual explanation. I hope you can see what I'm saying.
Yeah. Yeah, I can see it
Okay,
properly.
so we're actually using our example. So for this, they have 9.1. So converting
Mhm.
9, I don't think that's a big hassle for us. Then converting
Mhm.
zero point 0.1 now, um,
Mhm.
they have the same value we got here, not here, this. So we
But
have zero
uh-huh.
point 0.000110, yeah, and then it's repeating. And then
Mhm.
the fraction part, uh-huh. So this is
Mhm.
the integral part, this is the fraction part. So this is what the number would look like basically. And then
Yeah. Yeah.
now let's write this in scientific notation as below. Oh, wait. Even though 9 point,
Scroll up a little bit. What did they do? I'm trying to see. Trying to see.
yeah. So
Okay.
we've converted 9 already. So this is the value of 9,
Mhm.
and this is the value of
Mhm.
0.1. So it's nothing
Yeah.
different from what we are used to. So this is the value of 9. This is
Mhm.
the value of 0.1. Um,
Yeah, yeah.
Then here,
Mm-hmm.
even though 9.1 is an infinite binary number, we have only 23 bits to store it. Now let's write this in
Okay.
scientific notation as below. So for here, 9.1, so it is I believe this should be 2 power 3, the 2
One.
exponent of 3, 2 as the base, and then because it will make sense. So you see we have 3 here. So maybe the site didn't capture that
Uh. Okay.
thing
Okay.
correctly. So
Mm-hmm.
next, this number should be written in IE 754 format. So if the number is plus, the sign bit should be
Mm-hmm.
0. Oh, if the number is positive, the sign bit should be 0. If the number is negative, the sign bit should be 1. Oh, I guess we got that wrong. So according to our example, the
Yeah.
sign bit should be 0. Yeah,
Mm-hmm.
so 0 represents positive and then 1 represents negative. That's good to know. Then here, here exponent is an 8-bit value. Since this is a single precision value, therefore bias is 127. Now you should calculate the binary of bias plus exponent, as in here, 127 plus
Mm-hmm.
3. Yeah, exactly what we had done.
Mm-hmm. Mm-hmm.
And the binary of
Mm-hmm.
130 is this,
Yeah.
and this
Yeah.
is our exponent bias. Oh, which adds up
Mm-hmm.
according to that. So we have this. Okay,
Mm-hmm.
according oh, this is different because this is 9.1. Oh, it will be different from
Yeah.
what we have. Okay, okay.
Mm.
But that makes sense. And then I guess this is just them explaining what we've just done. And then now we have our mantissa,
Mm-hmm.
which is what is repeating here.
Yeah. Yeah.
Yeah, I think that makes sense. So we have our sign bit, we have our 8 bits telling us what exponent it is, and then we have our mantissa, which is basically what we've just conversion of a floating point number into binary. So the whole of this should
Yeah.
be a 32 bit,
Mm.
uh, 32 bits. So
Yeah.
I guess it comes at the end of the day, we end up with it's a pretty okay. First of all, this standard format is kind of genius. I like it. However, it
Mm-hmm.
doesn't solve all the problems when it comes
Yeah.
to calculating. So we get this unexpected value. So, but if you use
Mm-hmm.
a computer floating point converter to calculate this representation,
Readable, human readable